Right now, at this very moment, two spacecraft launched almost 50 years ago are still transmitting data back to Earth. They were designed to last 4 years. They have lasted nearly 5 decades. And what they have found at the outermost edge of our solar system has quietly rewritten our understanding of where the sun's influence ends and where true interstellar space begins. Voyager 1 is currently about 159 astronomical units from the sun. To put that in perspective, 1 astronomical unit is the average distance between the Earth and the sun, roughly 150 million kilometers. So Voyager 1 is now 159 times that distance away from our star. That is approximately 23.8 billion kilometers. It has taken the probe more than 48 years of continuous travel to reach that point, moving at roughly 17 kilometers per second, never slowing down, never stopping. And yet, despite that almost incomprehensible distance, Voyager 1 has not left the solar system, not even close. It crossed an important threshold, a boundary called the heliopause, but that boundary is not the edge of the sun's dominion. It is merely the edge of the solar wind's reach. Beyond the heliopause lies something else entirely, a region so vast, so ancient, and so far from any human instrument that we have never directly seen it. Scientists call it the Oort Cloud, and it may be the most significant structure in our solar system that almost nobody thinks about. To understand why crossing the heliopause was such a significant event, you first need to understand what the solar wind actually is. The sun is not a passive, stationary ball of light. It is an enormous nuclear reactor constantly ejecting matter in all directions. Every second, the sun fires a stream of charged particles outward at speeds ranging from 300 to 800 kilometers per second. This stream, called the solar wind, carries magnetic fields and energy with it, and it does not stop at the orbit of Pluto. It continues outward, gradually weakening, until the pressure of the surrounding interstellar medium finally overpowers it. The point where that balance occurs, where the sun's outgoing wind stalls and the interstellar medium takes over, is the heliopause. It sits at a distance of roughly 120 astronomical units from the sun, though this distance varies slightly depending on solar activity and the local density of interstellar gas. When Voyager 1 crossed this boundary in 2012, and Voyager 2 followed in 2018, the spacecraft recorded something unmistakable. Plasma density increased sharply, the magnetic field changed character, cosmic ray counts jumped, the physical environment of space changed dramatically in a very short distance. This was not a gentle transition, it was a wall. The instruments on both probes recorded a clear, abrupt shift in the properties of the surrounding medium. On one side was the heliosphere, the solar bubble. On the other side was something our spacecraft had never touched before, material that had never been processed by our sun, ancient gas and dust drifting through the interstellar medium, carrying the remnants of other stars, other explosions, other eras of galactic history. For the first time in the history of our species, human-built objects were sampling material from between the stars. That alone is extraordinary, but here is the thing that often gets overlooked. Even after crossing the heliopause, even after entering what scientists call interstellar space in the technical sense, Voyager 1 is still gravitationally bound to our sun. It has not escaped the solar system. It is still, in the most fundamental physical sense, a part of it. Between Voyager 1's current position and the true outer edge of the solar system, there exists a vast, dark, almost completely unexplored region that dwarfs everything between the sun and where Voyager is now. At its center of this region lies a hypothetical structure that no probe has ever reached, no telescope has ever directly photographed, and no astronomer has ever seen. And yet scientists are extraordinarily confident it exists. This is the Oort Cloud, and understanding it requires stepping back through history, following the path of comets across millennia. In the early 18th century, the English astronomer Edmund Halley was studying records of bright comets going back hundreds of years. In 1705, he realized something remarkable. The spectacular comets observed in 1682, in 1680, and back in 1607 were not separate objects. They were the same comet returning again and again on a roughly 75-year orbit. What we now call Halley's Comet had been witnessed by ancient Romans, medieval Europeans, and early modern astronomers, without anyone realizing they were seeing the same object. This discovery raised an immediate puzzle. If a comet passes close to the Sun every 75 years, the Sun's heat should gradually strip away its icy surface. The comet should have evaporated long ago. So how was it still there? The logical conclusion was that a comet must spend most of its time very far from the Sun, in a region cold enough to preserve its ice essentially forever. Only for a brief portion of its orbit does it swing inward, heat up, develop that glowing tail we see in the night sky, and then retreat back into the cold, dark outer solar system to wait another lifetime. For short-period comets like Halley's, with orbital periods of less than 200 years, this made sense. These objects orbit closer in, within a region beyond Neptune called the Kuiper Belt, a disc-shaped reservoir of icy bodies extending from roughly 30 astronomical units to about 50 astronomical units. Pluto is a Kuiper Belt object, so are hundreds of thousands of other bodies, including several dwarf planets. But astronomers also noticed a completely different category of comets, long-period comets. These objects have orbital periods measured not in decades, but in thousands or tens of thousands or even millions of years, and they behave completely differently from short-period comets. They do not arrive from the same flat plane where the planets orbit. They arrive from every direction, some from above the plane of the solar system, some from below, some swooping in at extreme angles, some even traveling in the opposite direction to the planets, a motion called retrograde orbit. This isotropic distribution, meaning roughly equal numbers coming from all directions, was the critical clue. If long-period comets originated from a disc-shaped region like the Kuiper Belt, you would expect them to arrive preferentially from the plane of the solar system. The fact that they arrive from all directions suggests their source is not a disk, but a sphere, a spherical reservoir surrounding the Sun in all directions equally. In 1950, a Dutch astronomer named Jan Oort examined the orbital data for long-period comets in detail and noticed something else remarkable. The farthest points of their orbits, called aphelia, tended to cluster at distances of around 50,000 astronomical units from the Sun, not at random distances, not scattered across all scales, but concentrated at a specific range. This was not a coincidence, it was a fingerprint. Something was out there at that distance, storing these icy bodies and occasionally sending them inward. Oort proposed the existence of a vast spherical cloud of icy objects surrounding the solar system at these enormous distances. His 1950 paper introduced the concept of what would become known as the Oort Cloud, and in a sense, it completed the picture of the solar system's outer architecture. Inside the heliopause, you have the heliosphere and the Kuiper Belt and the scattered disk. But beyond that, extending from roughly 2,000 astronomical units out to perhaps 100,000 or even more, lies this enormous, invisible reservoir. To appreciate how far away this actually is, consider the numbers carefully. 1 astronomical unit, the distance from Earth to the Sun, is about 150 million kilometers. The inner edge of the Oort Cloud is estimated to begin around 2,000 astronomical units from the Sun, that is approximately 300 billion kilometers. Already that is a distance so large it barely registers as a real number. But the outer edge of the cloud may extend to 100,000 astronomical units or more. That is roughly 1.5 light years from the Sun. The nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. If the Oort Cloud extends to 1.5 light years, then our solar system reaches nearly a third of the way to the nearest star. The Oort Cloud is not a minor feature at the edge of our planetary system. It is a colossal structure that makes our solar system far larger than most people realize. Now consider Voyager 1. Moving at 17 kilometers per second, the fastest human-made object ever launched, it has taken 48 years to travel 159 astronomical units. At that same speed, it would take approximately 300 years just to reach the inner edge of the Oort Cloud. And to cross through the cloud entirely and reach the outer edge would take around 30,000 years. The battery that powers Voyager's instruments will go dead around 2025. Its nuclear generators are already fadding. By the time it reaches the Oort Cloud, the probe will have been silent for 28,000 years. This scale is not abstract. It has direct implications for the possibility of ever sending a probe to actually study the Oort Cloud directly. With current propulsion technology, it is simply not possible within any realistic human timeframe. Any mission designed to reach the inner edge of the Oort Cloud would need to travel at speeds orders of magnitude greater than anything we have achieved. Even with future nuclear or ion propulsion systems under theoretical development, the inner Oort Cloud represents a target that is centuries away, not decades. In the spring of 2025, an automated telescope network called PANSDAIS detected a faint moving object in the outer solar system. As astronomers tracked its trajectory and computed its orbit, the numbers were striking. This object, designated Comet C 2025 R3, was approaching the inner solar system on a highly inclined orbit, tilted about 125 degrees relative to the plane of the ecliptic. That extreme inclination is a signature of Oort Cloud origin. Objects from the Kuiper belt tend to orbit close to the ecliptic plane. Objects arriving from the Oort Cloud can come from virtually any angle. The comet's trajectory brought it to perihelion, its closest approach to the Sun, on April 20, 2026, at a distance of approximately 0.51 astronomical units from the Sun, less than 80 million kilometers. 1 week later, on April 27, 2026, it passed closest to Earth at a distance of approximately 0.53 astronomical units. Under the right conditions, when a comet passes between Earth and the Sun at close range, sunlight reflecting off the dust tail can produce an effect called forward scattering, dramatically brightening the comet's apparent magnitude. This ancient, frozen visitor from the outermost reaches of our solar system may have been visible to the naked eye from Earth. Every comet like this is a physical sample of the Oort Cloud's contents, a frozen piece of the solar system's earliest history delivered directly to the inner solar system. When a comet develops its tail near the Sun, it is sublimating ice that has been preserved at temperatures near absolute zero for billions of years. The material in that tail has not been significantly altered since before the planets formed. It is primordial solar system material, and it is arriving for inspection at our doorstep. So what actually is the Oort Cloud made of? The short answer is, we believe it contains a mixture of ices, rocks, and organic compounds, broadly similar in composition to cometary nuclei, which is our only direct window into Oort Cloud material. The ices include water ice, frozen carbon dioxide, carbon monoxide, methane, and ammonia. Mixed in with these volatiles are silicate rocks and complex organic molecules. These are the basic ingredients of the outer solar system at the time of its formation, preserved in deep freeze for 4.5 billion years. Estimates of the total number of objects in the Oort Cloud range from tens of billions to possibly several trillion. Most are small, perhaps a few kilometers in diameter, similar in size to known cometary nuclei, but the range of sizes may be broader. Some researchers have proposed that the cloud could contain objects large enough to qualify as dwarf planets, bodies hundreds of kilometers across sitting in frozen darkness at distances so vast that no telescope has ever detected them. The total mass of the Oort Cloud is difficult to estimate because we cannot observe it directly. Calculations based on the observed rate of long-period comets arriving in the inner solar system suggest the cloud's total mass might be somewhere between a few Earth masses and several Earth masses. But this is a rough estimate with large uncertainties. In 2021, scientists got an unexpected hint that the Oort Cloud might be more compositionally diverse than previously thought. A fireball meteor event over Alberta, Canada, was tracked by multiple instruments, and its pre-impact trajectory was reconstructed. The object had come from the outer solar system on a highly inclined retrograde orbit, exactly the kind of trajectory you would expect from an Oort Cloud object. But when scientists analyzed the meteoroid's behavior as it penetrated the atmosphere, they found it was unusually dense and robust. It penetrated much deeper than an icy comet fragment would. The object was rocky, not icy. This was surprising. The prevailing assumption had been that the Oort Cloud was populated almost entirely with icy bodies, cometary nuclei, that had been ejected from the outer regions of the early solar system where ice condenses. The discovery of a rocky visitor from the Oort Cloud raised an intriguing possibility. Perhaps a small fraction of the cloud's population consists of rocky bodies ejected from the inner solar system during the chaotic early period of planetary formation, when gravitational interactions between the giant planets were reshaping the architecture of the solar system and flinging objects in all directions. Simulations of early solar system dynamics show that it was not only icy bodies from the outer regions that got ejected to great distances. Rocky material from the asteroid belt and even closer in could also have been scattered outward by close encounters with Jupiter or Saturn. If even a few percent of the Oort Cloud's population is rocky, and if the cloud contains trillions of objects, then the number of rocky bodies lurking out there is potentially enormous. The broader structure of the Oort Cloud is also more complex than a simple uniform sphere. Astronomers now think it likely has two main components. The outer Oort Cloud is the classical spherical shell that Oort originally described, extending roughly from 20,000 astronomical units to 100,000 astronomical units or more. This is the region where gravitational binding to the Sun is so weak that passing stars and the tidal forces of the Milky Way galaxy can easily perturb orbits and send objects plunging inward. The inner component, sometimes called the Hills Cloud after the astronomer Jack Hills, who proposed it in 1981, extends from roughly 2,000 to 20 distinct from outer cloud objects. The difference in shape between the inner and outer cloud is a result of different gravitational dynamics. Objects in the outer cloud are weakly held by the Sun. Even the gentle tidal force exerted by the overall mass distribution of the Milky Way galaxy, a force sometimes called the galactic tide, is strong enough to significantly perturb their orbits over millions of years. Stars passing through or near the outer cloud can scatter objects dramatically. Over billions of years, these forces have randomized orbital inclinations in the outer cloud, transforming what was originally a disc-shaped distribution of debris into something approaching a sphere. Objects in the Hills Cloud are held more firmly. The same galactic and stellar perturbations that scramble outer cloud orbits have a weaker effect on objects closer in. So the inner cloud may retain more of its original flattened distribution, a kind of bridge between the Kuiper belt and the spherical outer cloud. The mechanism by which the Oort Cloud originally formed is itself a story of violence and chaos. In the earliest epoch of the solar system, about 4.5 billion years ago, the region beyond Neptune was populated by enormous numbers of small icy bodies called planetesimals. These were the building blocks of the outer planets, the raw material left over after Jupiter, Saturn, Uranus, and Neptune accreted their bulk. As the giant planets settled into their current orbits, their enormous gravitational fields played havoc with the remaining planetesimals. Close encounters with Jupiter in particular were catastrophic for small bodies. Jupiter's gravity is so powerful that objects passing near it can be accelerated to escape velocity, flung into highly elongated orbits that carry them far from the Sun or ejected from the solar system entirely. Uranus and Neptune, being less massive and in the outer regions, were less efficient ejectors, but still contributed significantly to populating distant orbits. The result of this process, running over tens of millions of years, was that a substantial fraction of the outer solar system's original planetesimal population was thrown into orbits with aphelia at tens of thousands of astronomical units. These objects were not completely ejected. They were still gravitationally bound to the Sun, but barely. In this weakly bound state, they were vulnerable to outside influences. The Sun did not form in isolation. Like most stars, it was born in a cluster of hundreds or thousands of other stars. For the first few 100 million years of the solar system's history, these neighboring stars were relatively close. Stellar flybys, passages of other stars within a light year or two of the Sun, would have been common events. Each flyby would have gravitationally stirred the orbits of the outermost bodies, gradually randomizing their inclinations and orientations. Over time, the galaxy's tidal force continued this randomization process. The end result was the spherical cloud we infer today. A particularly interesting case is Scholz's star, a nearby red dwarf that passed through the outer Oort Cloud approximately 70,000 years ago, coming within an estimated 0.8 light-years of the Sun. Anatomical analysis of its trajectory reconstructed this close approach. Scholz's star's passage would have perturbed the orbits of objects in the outer cloud. The effects were probably not catastrophic, but such events, occurring repeatedly over billions of years, cumulatively sculpted the cloud's current structure. Now consider this from the perspective of other star systems. Our Sun went through this process, so should other stars. The same physical mechanisms, giant planets ejecting planetesimals, stellar flybys scattering them into spherical distributions, galactic tides maintaining the scatter, should operate in any planetary system. This means that virtually every star with a planetary system should have its own version of the Oort Cloud. Astronomers call these hypothetical structures exo-Oort clouds, and the evidence for them, while indirect, is growing. When astronomers observe comets falling onto other stars, or when they detect extended disk structures around other stellar systems that cannot be explained by the more compact Kuiper belt analogues, these observations hint at distant reservoirs similar to our own cloud. Some stellar systems even show evidence of material being actively stirred inward from great distances, consistent with gravitational perturbations acting on an exo-Oort cloud. A particularly ambitious idea proposed in 2018 suggested that a sufficiently large exo-Oort cloud around a nearby star might leave a detectable imprint on the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. The proposal was that a shell of cold dust and ice at great distances from a star could very slightly absorb or scatter microwave radiation, creating a tiny but potentially detectable shadow. Analyzing data from the Planck satellite with this idea in mind could, in principle, reveal traces of such structures around nearby stars. This kind of indirect detection is exactly how the Oort cloud around our own Sun was first established. Jan Oort did not see the cloud directly. He inferred it from the orbital distribution of the comets we could observe. The comets were messengers carrying information about a structure far too faint and distant to observe directly. This is a profound example of scientific inference. You do not always need to see a thing to know it is there. You need only to understand what its effects should look like, and then identify those effects in the data you can access. The same logic that allowed us to confirm the existence of Neptune before direct observation by analyzing unexplained perturbations in Uranus's orbit applies here. Neptune's gravitational fingerprint was visible in the motion of Uranus. The Oort cloud's gravitational fingerprint is visible in the arrival directions and orbital characteristics of long-period comets. Speaking of Uranus, the planet offers its own remarkable lesson about the difficulty of interpreting planetary data under unusual conditions. When Voyager 2 made its only flyby of Uranus in January of 1986, it gathered the only close-up observations of that planet ever made by a spacecraft. The data seemed to paint a picture of an unusual magnetosphere, weaker than expected, with low plasma concentrations and an oddly intense radiation belt. For decades, scientists interpreted these observations as telling us something fundamental about Uranus itself, something strange about the planet's magnetic environment. But a study published in Nature Astronomy in recent years revealed that the flyby occurred under exceptionally unusual circumstances. In the days just before Voyager 2's arrival, the Sun experienced an unusually intense burst of solar activity, driving a surge of solar wind pressure that temporarily compressed Uranus's magnetosphere to roughly 20% of its normal volume. Under normal conditions, Uranus's magnetosphere extends about 22 to 25 planetary radii outward from the planet. During the flyby, the magnetopause, the boundary where solar wind pressure and magnetic pressure balance, was compressed inward to about 17.3 planetary radii. The extreme solar wind had also likely pushed plasma out of the magnetosphere, making the region appear abnormally sparse in charged particles. The unexpected radiation belt behavior may have been a direct consequence of this compression rather than a permanent feature of Uranus's magnetic environment. In other words, Voyager 2 arrived at exactly the wrong moment, during a solar weather event that occurs only about 4% of the time. It observed Uranus in an abnormal state, and because it was the only flyby ever made, that abnormal state became the basis for our entire understanding of Uranus's magnetosphere for the next 40 years. This is a sobering reminder of how incomplete any snapshot observation can be. A single measurement made at a single moment under unusual conditions can create false impressions that last decades. Proposed Uranus orbiter and probe, which has been at the top of NASA's planetary science priority list for the next decade, would remedy this situation enormously. Extended observation over many years and many solar wind conditions would allow scientists to characterize Uranus's true magnetic environment, understand the behavior of its moons, and perhaps finally make sense of the planet's extreme axial tilt, one of the most puzzling features in the entire solar system. The Voyager missions also introduced humanity to 2 interstellar visitors that arrived in our solar system from beyond its boundaries entirely. In late 2017, the object now designated ʻOumuamua was discovered by astronomers using the Pan-STARRS telescope in Hawaii. It was moving too fast to be bound to the Sun. Its trajectory was hyperbolic, meaning it was passing through our solar system on a one-way trip, having arrived from interstellar space and destined to return to it. It was the first confirmed interstellar object ever detected passing through our solar system. Oumuamua was strange in many ways. It was extremely elongated or possibly flat and disk-like, unlike any known comet or asteroid. It showed anomalous acceleration away from the Sun that could not be explained by gravitational forces alone. When scientists looked for outgassing of the kind that drives cometary acceleration, they found none. The source of the acceleration remains debated. 2 years later, in 2019, a more clearly cometary interstellar visitor arrived. Comet 2I Borisov was discovered by the amateur astronomer Gennady Borisov before it had entered the inner solar system. Unlike Oumuamua, Borisov displayed clear cometary activity, sublimating ices as it approached the Sun and forming a coma and tail. Spectroscopic analysis revealed its composition, including an unusually high abundance of carbon monoxide relative to water ice. This composition was somewhat different from typical solar system comets, hinting that Borisov formed around a different type of star in a different chemical environment. These interstellar visitors are significant for several reasons. First, they confirm that objects do travel between star systems, cast off from their home systems during planetary formation and drifting through interstellar space until they happen to pass through another system. This means that the Oort Cloud analogues around other stars may exchange material with our own cloud over the history of the galaxy. Some long-period comets arriving in our solar system might actually originate from other stellar systems, having been captured into bound orbits by gravitational interactions in the early solar system when stars were much more densely packed together. The vast majority of long-period comets follow orbital patterns consistent with an origin in our own Oort Cloud. Their distribution in aphelion distance, their isotropic arrival directions, and their abundance all fit the model. Interstellar interlopers are rare, but their existence proves that the universe is not as isolated as it might appear. Star systems are not hermetically sealed. They leak material into interstellar space and occasionally catch material drifting in from others. Could there be larger objects in the Oort Cloud? Objects massive enough to qualify not as comets or even dwarf planets, but as captured rogue planets. This is not idle speculation. A 2023 study examined the dynamics of early star cluster environments and found that when stars form in clusters, as the Sun did, gravitational encounters between neighboring systems can result in the capture of ejected planets. A planet thrown out of one system by its giant planets might wander through interstellar space and eventually be captured into a distant orbit around another star. The simulations found that the probability of our Sun having captured a planet during its time in the birth cluster is roughly 7%. That is a surprisingly high probability. Such a captured world would end up in exactly the kind of distant, weakly bound orbit that characterizes the Oort Cloud region. It would be extraordinarily faint and far away, essentially undetectable with any current technology. But if it exists, it would be a world of another sun, orbiting ours in the dark. The same study found that the probability of one of our own original planets having been ejected outward to Oort Cloud distances is much lower, only about 0.5%. So if there is a large object out there, it is more likely to be a captured stranger than an exiled native. This is a distinction that would have profound implications if such an object were ever confirmed. The question of undiscovered large objects in the outer solar system has become more pressing in recent years due to the Planet 9 hypothesis. Astronomers studying the clustering of orbits among distant Kuiper belt objects noticed that several of these objects have orbital parameters that are statistically unlikely to have occurred by chance. One explanation for this clustering is that a large, unseen planet, possibly 5 to 15 times the mass of Earth, is shepherding these objects gravitationally from a distant orbit. The hypothetical Planet 9 is thought to orbit at hundreds to perhaps 1,000 or 2,000 astronomical units, placing it in the region between the Kuiper belt and the inner Oort Cloud. Planet 9, if it exists, would still be too close to qualify as an Oort Cloud object in the classical sense, but its gravitational influence might extend into the Hills Cloud, affecting the orbital evolution of objects there. The search for Planet 9 continues, though its existence remains unconfirmed. NASA's WISE Infrared Telescope survey, conducted in 2010 and 2011, ruled out the existence of any Jupiter-sized or larger object in the outer solar system. So whatever might be lurking there, it is not a gas giant of that scale. What is certain is that we are extraordinarily ignorant about the outer solar system. The Kuiper belt was not even confirmed to exist until 1992, when the first Kuiper belt object beyond Pluto was discovered. Before that, for decades, Pluto was thought to be a lone oddity in the outer solar system. The discovery of the Kuiper belt transformed our picture of the solar system's structure almost overnight. A similar revision could occur if and when the Oort Cloud yields its first directly observed object, or if a large undiscovered body is confirmed in the outer regions. The technology required to directly detect Oort Cloud objects is formidable. A typical Oort Cloud object might be a few kilometers in diameter, dark in color, and located at distances of 10,000 to 50,000 astronomical units. At that distance, even a relatively large object reflects so little sunlight that it would be invisible to current telescopes. Even the Vera C. Rubin Observatory, currently the most powerful wide-field survey telescope ever built, is not expected to directly detect individual Oort Cloud objects in the outer cloud. It might catch a few unusually large objects in the inner Hills Cloud region, but the main population of the Oort Cloud remains beyond reach. The paradox is that we know the Oort Cloud is there with high confidence, yet we cannot see it. Every long-period comet that blazes through the inner solar system is, in effect, a sample returned from the Oort Cloud, a piece of the cloud's content delivered to us for analysis. But we cannot choose which samples to collect. We can only analyze what arrives. We cannot go to the source. The discovery of comet C 2025R3 in 2025 gave astronomers another such sample. Its high inclination and retrograde orbit strongly suggested an Oort Cloud origin. Its chemical composition, analyzed as it approached the Sun and heated, provided data on the volatile inventory of Oort Cloud objects in its region. Every such comet adds to a growing, if still incomplete, catalogue of Oort Cloud material. Understanding the Oort Cloud is not merely an academic exercise. The cloud is the primary reservoir from which long-period comets originate, and comets have played a significant role in the history of life on Earth. Comets deliver organic molecules and water to planets. The early Earth was heavily bombarded by comets and asteroids during a period called the Late Heavy Bombardment, approximately 4 billion years ago, and comets may have contributed substantially to Earth's water inventory and to the organic chemistry that preceded life. Conversely, comets are also potential impactors. A comet on a trajectory toward Earth is a different kind of hazard than an asteroid. Asteroids in the near-Earth asteroid population are continuously tracked and catalogued by observational programs. We now know the orbits of hundreds of thousands of them with enough precision to predict close approaches decades in advance. But long-period comets arriving from the Oort Cloud are different. They arrive with little warning, sometimes only months or a year or two between discovery and closest approach, because they spend most of their orbit in the cold darkness far beyond any current detection capability. If a long-period comet were on a collision course with Earth, our warning time might be dangerously short. This is not a theoretical concern. Comet impacts have occurred throughout Earth's history and have had dramatic effects. The development of better survey telescopes capable of detecting comets earlier in their inbound trajectories is an active area of planetary defense planning. The Oort Cloud is also intimately connected to questions about the Sun's history and its journey through the galaxy. The Sun does not sit still at the center of the Milky Way. It orbits the galactic center at a speed of about 220 kilometers per second, taking about 225 million years to complete one orbit. During this journey, it moves through different regions of the galaxy, encountering varying stellar densities, crossing the spiral arms, and experiencing different tidal environments. Periods when the Sun passes through denser regions of the galaxy, such as the spiral arms, may correspond to increased rates of stellar flybys past the Oort Cloud. This would stir up the cloud, sending showers of comets toward the inner solar system. Some researchers have proposed that periodic comet showers, separated by intervals of roughly 26 to 30 million years, could explain periodic mass extinction events in Earth's fossil record. The evidence for this periodicity is disputed, and the causal chain involves many assumptions, but the basic physics of how galactic environment can modulate Oort Cloud disturbances is sound. Oort Cloud, then, connects the history of the solar system to the history of the galaxy. It is a structure shaped by stellar encounters, galactic tides, and the dynamics of the early solar system. It is a reservoir of primordial material preserved since before Earth existed. It is a potential source of cosmic bombardment that may have influenced the course of evolution on our planet. And it is a structure so vast that even our fastest spacecraft would take 30,000 years to cross it. Voyager 1, currently traveling through interstellar space in the strict sense that it has crossed the heliopause, is still gravitationally speaking a part of this solar system. It is still within the Sun's domain. The Oort Cloud begins where Voyager cannot reach for 300 more years, and it extends to distances that would take Voyager more than 30,000 years to traverse. The probe will be silent before it covers 1% of that journey. We have reached the edge of the solar wind. We have never touched the true edge of the solar system. Those are very different things, and the difference between them is, in human terms, essentially infinite. What comes next in our understanding of the Oort Cloud will depend on advances in several areas. Better survey telescopes may begin to detect Hills cloud objects, the inner population, which are closer and somewhat more detectable. Advanced space telescopes operating in the infrared might catch the thermal glow of larger Oort Cloud bodies against the cold background of deep space. Future spacecraft with dramatically improved propulsion technology could be directed toward the inner cloud as a long-duration mission, similar to how New Horizons was sent to Pluto, but requiring far more patience and far more engineering ingenuity. Perhaps most importantly, every long-period comet that arrives in the inner solar system will continue to be analyzed with increasingly powerful instruments. Chemical spectrometers that can characterize comet composition in precise detail are becoming standard tools at major observatories. Each new comet is a unique sample from a different part of the cloud, formed under potentially different conditions and carrying its own record of the early solar system's chemistry. The interstellar visitors, ʻOumuamua and Borisov, have also opened a new field of inquiry. Objects traveling from other stellar systems may pass through the inner solar system at rates higher than previously thought. Some estimates suggest there could be several interstellar objects passing through the inner solar system every year, most of them too small to detect with current instruments. A proposed mission called the Comet Interceptor, currently under development by the European Space Agency, is designed to sit in readiness at a gravitationally stable point in space, and then be redirected to intercept either a newly discovered long-period comet or an interstellar object if one is detected with enough advance notice. If such a mission succeeds in intercepting a truly pristine long-period comet, the scientific return would be extraordinary. We would have direct, in-situ measurements of an object that formed 4.5 billion years ago and has spent almost all of that time in the deep freeze of the Oort Cloud. Its surface and interior would record conditions in the early solar system that no amount of remote observation can replicate. This is the frontier of solar system science, not the planets, not even the Kuiper belt, but the vast, dark, immeasurably ancient structure that wraps around everything we have ever explored. The Oort Cloud is not a footnote to the solar system. It is, by volume, most of it. The next time a bright comet appears in the night sky, visible to the naked eye, drawing attention from people who have never thought about it before, consider where it has been. That comet has likely been drifting in darkness at a distance of tens of thousands of astronomical units for 4 billion years, preserved in cold so extreme that the chemistry of its surface has barely changed since before the first living cell appeared on Earth. A gravitational nudge from a passing star or the gentle pull of the galactic tide set it on its current path. It has been falling inward for millions of years, and now, briefly, it swings through our neighborhood, heats up, develops its glowing tail, and becomes visible from the surface of a planet where beings have evolved the capacity to wonder where it came from. It came from the beginning, from the outer darkness that is most of our solar system, from a structure so large and so remote that we have only ever known it through inference and calculation, never through direct sight. The Oort Cloud is the largest thing in the solar system. It is also the least seen, and it is out there, right now, in all directions, surrounding everything we have ever known. If you find this kind of deep exploration of our cosmic neighborhood as fascinating as we do, consider subscribing so you never miss the next time science reveals something extraordinary about the universe we inhabit. To truly appreciate what the Oort Cloud represents in the grand context of solar system science, it helps to step back and consider the full history of how humanity has discovered the architecture of our local corner of the cosmos. For most of human history, the solar system was thought to consist of the planets, their moons, and the sun. Everything else was assumed to be empty space. The idea that there could be vast populations of small bodies extending to enormous distances, invisible to the eye and barely detectable even to the best telescopes, would have seemed absurd to astronomers of the 19th century. The shift began with the systematic discovery of asteroids in the early 1800s. After the Italian astronomer Giuseppe Piazzi discovered Ceres in 1801, astronomers expected to find a single missing planet between Mars and Jupiter. Instead, they found dozens, then hundreds, then thousands of objects, all occupying a broad band of space in nearly the same orbital plane as the planets. The asteroid belt was not a planet. It was a population of surviving debris from the early solar system, material that was never able to coalesce into a planet because Jupiter's gravitational influence kept stirring it up and preventing accretion. This discovery established an important principle. The solar system is not just planets and empty space. It is structured in layers with distinct populations of small bodies at different distances and in different configurations. The asteroid belt was the first such population recognized. The Kuiper belt was the second. The Oort Cloud is the third, and by far the most remote and least understood. The discovery of the Kuiper belt was itself a long time coming. For years after Pluto's discovery in 1930, many astronomers assumed that Pluto was an isolated oddity, a small world that somehow ended up alone in the outer solar system beyond Neptune. A few theorists, including the Irish astronomer Kenneth Edgeworth in 1943 and the Dutch-American astronomer Gerard Kuiper in 1951, independently suggested that a disk of icy debris should exist beyond Neptune as a remnant of the solar system's formation. But for decades, no observational confirmation came. Then in 1992, astronomers David Jewett and Jane Liu, working with a sensitive camera on the University of Hawaii telescope atop Mauna Kea, discovered the first confirmed trans-Neptunian object beyond Pluto. The object, designated 1992 QB1, was small, cold, and dim, but it was clearly orbiting in the region beyond Neptune in a low-inclination orbit, consistent with Edgeworth and Kuiper's predictions. The floodgates opened. Within years, hundreds of Kuiper belt objects had been identified. Today the count stands in the hundreds of thousands, with more discovered regularly by increasingly powerful surveys. The Kuiper belt's discovery did more than just confirm a theoretical prediction. It forced a rethinking of Pluto's status. Pluto is not a unique oddity. It is one of the largest known Kuiper belt objects, a dwarf planet among hundreds of thousands of similar, if smaller, bodies. In 2006, the International Astronomical Union formally reclassified Pluto as a dwarf planet, a decision that generated more public controversy than perhaps any other astronomical reclassification in history. But scientifically, the change made perfect sense. Pluto belongs to a population. It is not a planet in the same category as Neptune or Jupiter. It is the brightest and most famous member of a vast icy disk. This history matters for the Oort Cloud because it illustrates a pattern. Theorists predict a population of distant bodies. Observational astronomers struggle for years or decades to confirm it. Then, when technology finally catches up, the population is revealed to be larger and more complex than initially imagined. The Oort Cloud fits this pattern exactly, but we are still in the waiting phase. We are at the point in the story where the theoretical prediction exists, supporting evidence is strong, but direct observational confirmation of the cloud as a coherent structure has not yet arrived. What would it take to actually see the Oort Cloud? The simplest way to think about this challenge is to consider the physics of detection. A telescope can detect an object in the outer solar system if either the object reflects enough sunlight back toward Earth, or if the object emits enough thermal radiation to be detected by an infrared instrument. Both quantities decrease rapidly with distance. Sunlight falls off as the inverse square of distance from the Sun. An object at 10,000 astronomical units receives 100 million times less sunlight than an object at 1 astronomical unit. Most of that already tiny amount of light hits the surface of the Oort Cloud object and is absorbed rather than reflected. The fraction that is reflected, called the albedo, depends on the surface composition. Typical cometary nuclei have very low albedos, around 4 to 6%, meaning they reflect only 4 to 6% of the light that hits them. The reflected light then has to travel back across 10,000 astronomical units to reach a telescope on Earth, diminishing again as the inverse square of that distance. The total signal available is so small that it is below the detection threshold of any current survey telescope at distances beyond the inner Hills cloud. Thermal emission is somewhat more promising for very large, warm objects, but Oort Cloud bodies at their typical distances are cold, around 10 to 20 degrees Kelvin above absolute zero, and emit most of their thermal radiation at wavelengths in the far infrared or submillimeter range, where our current telescopes have limited sensitivity. Future missions, like the proposed next-generation infrared space telescope surveys, could push detection limits further. Space-based infrared observatories are far more sensitive to cold, distant objects than ground-based optical telescopes, because the Earth's atmosphere absorbs much of the infrared light from space, and because the warm atmosphere itself emits infrared radiation that overwhelms faint signals from cold objects. A sufficiently powerful infrared space telescope operating at low temperatures could potentially detect the largest Oort Cloud objects, perhaps those hundreds of kilometers in diameter, out to distances of several thousand astronomical units. but detecting the main population of smaller, kilometer-scale objects in the outer cloud is probably many generations of technology away. The scientific importance of eventually solving this observational challenge cannot be overstated. The composition and total mass of the Oort Cloud is a record of the conditions in the outer protoplanetary disk where the solar system formed. The ratio of different ices, the abundance of organic compounds, the ratio of rocky to icy material, the size distribution of objects from cometary nuclei up to dwarf planets. All of these carry information about the temperature, density, and chemical environment of the outer solar system 4.5 billion years ago. Some of the most intriguing data about this early environment comes from the comets we can observe. Studies of cometary composition have revealed a rich suite of organic molecules, including amino acid precursors, simple sugars, and complex carbon compounds. The Rosetta mission, operated by the European Space Agency, spent 2 years in close proximity to Comet 67P Churyumov-Gerasimenko, a short-period comet from the Kuiper belt, and detected over 400 distinct organic molecules in the comet's outgassing. Among these were compounds relevant to biochemistry, including glycine, the simplest amino acid. Long-period comets from the Oort Cloud may carry an even richer inventory of organic compounds, having spent more time in the cold outer regions where complex chemistry can accumulate on grain surfaces. When such comets impact a planet or pass close enough to deposit material through meteoritic infall, they are delivering packages of prebiotic chemistry. Whether this delivery mechanism played a role in seeding Earth with the organic building blocks of life is one of the central open questions in astrobiology. The connection between comets and life on Earth runs even deeper than organic chemistry. Water is the most essential ingredient for life as we know it, and Earth's water supply is in some ways a mystery. Earth formed in the inner solar system, inside the snow line, the boundary beyond which water ice is stable. Material that accreted to form the Earth should have been relatively dry, yet Earth has enormous amounts of liquid water on its surface and dissolved in its rocks. Where did it come from? One significant source was comets. Comets are largely composed of water ice. Impacts of comets on the early Earth could have delivered enormous quantities of water, but there is a subtlety. Water in Earth's oceans has a specific ratio of deuterium to hydrogen, a signature that depends on where in the solar system the water formed. Measurements of cometary water from short-period comets initially showed a higher deuterium ratio than Earth's water, suggesting comets from the Kuiper belt were not the primary source. But measurements of longer-period comets and of the specific comet 103P Hartley 2, another short-period comet with an unusual chemical signature, suggested some comets do match Earth's water ratio. The debate about cometary water delivery is ongoing, but it illustrates how deeply the history of the outer solar system, including the Oort Cloud, is intertwined with the history of Earth and life. The cloud is not just an interesting distant curiosity. It is part of the story of why Earth is a habitable world. The dynamical history of the Oort Cloud is also linked to one of the most dramatic events in our solar system's past, the so-called Late Heavy Bombardment. This period, roughly 4 billion years ago, was characterized by an intense increase in the rate of impacts on the inner planets, the Moon, Mars, and Earth. The lunar surface bears the scars of this bombardment in the form of enormous impact basins, many of which were later flooded with volcanic lava to form the dark plains visible from Earth with the naked eye. The cause of the late heavy bombardment is debated. One influential model, called the Nice model after the city in France where it was developed, proposes that a dramatic reorganization of the orbits of the giant planets occurred roughly 700 million years after the solar system formed. In this scenario, Jupiter and Saturn crossed a 2-to-1 resonance in their orbital periods, triggering a cascade of orbital instabilities that sent Uranus and Neptune migrating outward, scattering vast numbers of Kuiper belt objects and Oort Cloud objects inward toward the inner solar system. The resulting surge of comet and asteroid impacts would have pounded the inner planets for hundreds of millions of years, explaining the intense crater record on the Moon. If this model is correct, the current structure of the Oort Cloud is partly a product of that event, shaped by the gravitational reshuffling that followed the giant planet migration. Some objects were ejected from the cloud, some were scattered into it, and the cloud we see today, inferred from long-period comets, reflects the aftermath of this violent rearrangement. More recent dynamical models have modified the NICE scenario in various ways, and the exact timing and sequence of events remains a subject of active research. But the core insight stands. The Oort Cloud is not a static structure that has sat undisturbed since the solar system's birth. It has been sculpted by billions of years of gravitational perturbations, stellar flybys, galactic tides, and the migration of the giant planets themselves. Its current state is the cumulative result of this long history. One aspect of the Oort Cloud that receives less attention than it deserves is its potential role as a trap for dark matter. The solar system moves through the Milky Way's dark matter halo, the vast invisible structure that provides the gravitational scaffolding for the galaxy's rotation. Most dark matter passes through the solar system without interaction, but theoretical models suggest that a small fraction might be captured into orbits around the Sun through a process of gravitational energy exchange with planets or other massive bodies. If dark matter particles can be captured into bound orbits, they would naturally settle into a diffuse cloud around the Sun, occupying the region of highest gravitational binding, which extends into the Oort Cloud zone. Some models of self-interacting dark matter predict that such captures could build up detectable concentrations of dark matter in the outer solar system over the lifetime of the Sun. While this remains highly speculative, it adds another dimension to the Oort Cloud's potential significance as a possible probe of dark matter properties that would be very difficult to test by other means. The galactic context of the Oort Cloud also deserves more attention. The Sun's position in the Milky Way places it roughly 26,000 light-years from the galactic center, in a relatively quiet region between two spiral arms. This location means that the Sun encounters relatively few other stars compared to what stars near the galactic center experience. In denser stellar environments, Oort clouds around other stars would be subjected to much more frequent and intense perturbations, sending cometary showers inward much more regularly. This suggests that planets orbiting stars in the inner galaxy would experience far higher rates of cometary bombardment than Earth has experienced. The implications for habitability are complex. More frequent cometary impacts would deliver more organic material and water, but would also cause more frequent mass extinction events. There may be a galactic habitable zone, a range of distances from the galactic center where stellar densities are high enough to enable the heavy element abundances needed for rocky planets, but not so high that cometary bombardment rates are catastrophically elevated. The Sun's current position and the relatively benign rate of perturbation to our Oort Cloud may be one factor among many that has made Earth a favorable environment for the long-term evolution of complex life. Understanding the Oort Cloud and how its perturbation rate depends on the Sun's galactic environment is therefore relevant to the broader question of why life exists where it does in the universe. There is also the question of what happens to the Oort Cloud in the very long term. The Sun is currently in the middle of its main sequence lifetime, burning hydrogen in its core and expected to continue doing so for another 5 billion years. In roughly 5 billion years, the Sun will exhaust its hydrogen, expand into a red giant, engulf the inner planets, and eventually shed its outer layers to leave behind a white dwarf. During the red giant phase, the Sun's radiation pressure and mass loss will profoundly alter the dynamics of the outer solar system. The mass loss will reduce the Sun's gravitational hold on distant objects. The Oort Cloud, already weakly bound, will be largely dispersed. Objects in the outer cloud will drift away into interstellar space. The inner Hills cloud might partially survive, but even it will be strongly perturbed by the solar mass loss and the eventual transition to a white dwarf. What remains of the Oort Cloud around a white dwarf would be drastically depleted, and would continue to be eroded by perturbations from passing stars over billions of years. In the very long run, over timescales of tens of billions of years, even white dwarfs and their remnant planetary systems will be disrupted by the gravitational effects of the galaxy. The Oort Cloud, like all structures in the universe, is temporary on a sufficiently long timescale. But we are 4.5 billion years into a 10 billion year main sequence lifetime, with 5 billion more years to go. For all practical purposes, the Oort Cloud has been here for as long as Earth has existed, and it will be here for as long as Earth will exist in anything like its current form. It is, for the duration of Earth's habitable epoch, a permanent fixture of the solar system. The Oort Cloud also speaks to a broader truth about scientific knowledge. We tend to think of what we know as the relevant territory and what we do not know as a kind of background noise. But in the case of the solar system, the reverse is true. The regions we understand well, the inner planets, the asteroid belt, the outer planets, the Kuiper belt, represent an extremely small fraction of the total volume and mass budget of the solar system. The Oort Cloud, which we understand only indirectly, contains more volume than everything else combined. It may contain more total mass than the Kuiper belt. It is, in a very real sense, most of the solar system. This is humbling. 5 decades of space exploration, including robotic missions to every planet, multiple visits to asteroids and comets, probes that have exited the heliosphere, have explored a tiny fraction of our own solar system. The vast majority remains unknown, unseen, and unreachable with any technology we can build today. The Oort Cloud is not the edge of the frontier. It is the frontier itself. It is also worth considering what the Oort Cloud means for the concept of the solar system as a discrete, bounded object. In everyday thinking, we tend to imagine the solar system as a defined region, like a country with borders. The planets are inside it. Interstellar space is outside it. But the Oort Cloud blurs this distinction dramatically. Its outermost objects are so weakly bound to the Sun that they are barely distinguishable from free-floating objects in interstellar space. Some may have been exchanged between our system and neighboring systems. Interstellar objects passing through our system get temporarily perturbed into bound-like trajectories before eventually escaping. The boundary between the solar system and interstellar space is not a sharp line. It is a broad, gradual, constantly shifting transition zone. This fuzziness is not a problem for physics. Gravity does not recognize borders. Objects can be gravitationally associated with the Sun to varying degrees, from the tight orbits of Mercury at fractions of an astronomical unit out to the barely bound objects at the outer Oort Cloud. The cloud is not a sharp feature. It is the continuation of a gravitational gradient that starts at the Sun's surface and extends almost to the nearest star. Understanding the Oort Cloud, therefore, is not just about cataloging a distant population of icy bodies. It is about understanding the nature of the solar system's boundary, the Sun's relationship to the galaxy, the history of the solar system's formation and dynamical evolution, and the environmental factors that have shaped the history of life on Earth. Few structures in astronomy connect so many fundamental questions across so many different timescales. Voyager 1 has crossed the heliopause. It is transmitting data from interstellar space. Scientists are analyzing those transmissions right now, extracting information about the plasma density, the magnetic field, and the cosmic ray environment of the interstellar medium immediately outside the solar bubble. It is, by any measure, an extraordinary achievement. A machine built in the early 1970s, launched before personal computers existed, before the internet existed, before the human genome had been sequenced, is still operating and returning scientific data nearly a half-century later. But it is important to hold two truths simultaneously. Voyager 1 has done something remarkable, and Voyager 1 has barely left the solar system. The heliopause is not the edge. The Oort Cloud, which begins where Voyager cannot arrive for 3 more centuries, is the edge. And even the edge of the Oort Cloud is not the edge of the Sun's gravitational domain. These are not contradictory facts. They are a measure of the scale of what we are embedded in. The solar system is not a small, easily traversed neighborhood. It is a structure of almost incomprehensible extent, most of which we have never seen, most of which we cannot reach, and most of which we will never directly explore. The Oort Cloud is the reminder that the universe does not scale to human ambition. It scales to physics, and physics operates on timescales and distances that reduce everything we have accomplished to a first, tentative step. The Voyager probes will eventually fall silent. Their plutonium-238 power sources are already diminishing. Sometime around 2025 or 26, the last instruments will lose power and the spacecraft will continue outward in silence, their radio transmitters dead, their cameras staring into darkness. They will drift for millions of years, carried by the gravity of the sun and perturbed by stars they will pass, falling through the Oort Cloud, eventually reaching the inner Oort Cloud around the year 2326, continuing through the cloud for the next 20 or 30,000 years, and eventually, if they survive without a significant collision, reaching the outer edge of the solar system's gravitational influence around the year 32,000. By that time, humanity, if it still exists, will be unrecognizably different from what we are today. The probe's origin will be as remote in time as the invention of writing is to us now, more remote than all of recorded human history. And yet there it will be, a machine made of aluminum and gold and copper and silicon, built by human hands on a small planet orbiting an ordinary star, drifting through the outermost edge of the very system that star created. This is what the Oort Cloud represents in the deepest sense. It is not just a scientific mystery waiting to be solved. It is a measure of the distance between what human civilization has achieved and what the universe actually contains. It is the reminder that exploration is not a finite task. It is an open-ended engagement with a universe that is always larger, always older, and always more strange than any map we have drawn of it so far. The comets will keep arriving. Each new one will carry its message from the outer darkness, its frozen record of conditions 4.5 billion years ago, its chemical inventory of the early solar system. We will read those messages with every instrument at our disposal. We will refine our models of the cloud's structure, mass, and composition. We will build better telescopes and better spacecraft and better theories. And perhaps, in a century or 2 or 5, we will finally design a mission that can reach the inner Oort Cloud within a human lifetime. And humanity will see, for the first time, the objects Jan Oort inferred from his analysis of cometary orbits in 1950. Until that day, the Oort Cloud remains what it has always been, the largest, darkest, most ancient, and least known part of our home system. It is out there in every direction, above and below and all around us, a sphere of frozen time surrounding a small, warm, luminous star and all the worlds that orbit it, including ours. To fully grasp the scientific significance of the Oort Cloud, it helps to understand the broader context of solar system formation, because the cloud is not merely a byproduct of that process. It is a direct record of it. Our solar system began as a rotating disk of gas and dust, called a protoplanetary disk, surrounding the young sun approximately 4.5 billion years ago. The inner regions of this disk, where temperatures were high, produced rocky planets from silicates and metals that could survive the heat. The outer regions, beyond the frost line where temperatures dropped low enough for water ice to condense, produced icy bodies and eventually, through accretion of gas and ice, the giant planets. The formation of Jupiter was particularly significant for everything that came after. Jupiter is so massive, containing more than twice the mass of all other planets combined, that its gravitational field dominated the dynamics of the outer solar system from a very early stage. As Jupiter was assembling itself, its growing gravitational influence began ejecting smaller bodies from the surrounding region. Icy planetesimals that strayed too close to Jupiter were flung onto highly elongated orbits, some being ejected from the solar system entirely, others being placed in distant, weakly bound trajectories that would become the Oort Cloud. Saturn, Uranus, and Neptune played similar roles to a lesser degree. The giant planet formation process was, from the perspective of everything else in the outer solar system, a period of violent, chaotic sorting. Billions of small icy bodies were scattered in all directions. Most were ejected into interstellar space entirely, lost forever. The ones that managed to remain just barely bound to the sun populated the distant reservoir that Jan Oort would recognize billions of years later from the orbital patterns of returning comets. This picture has been refined enormously in recent decades by computer simulations of planetary formation and orbital dynamics. The Grand TAC model, for example, proposes that Jupiter initially formed further out than its current position, then migrated inward toward the Sun before being pulled back outward by Saturn's gravity. This inward and outward migration, like a tack in sailing, would have dramatically scattered the asteroid belt and outer solar system populations, potentially mixing material from different regions and modifying the populations of both the Kuiper belt and the Oort Cloud. The dynamical simulations required to model these events are enormously complex, tracking the gravitational interactions of millions of bodies over hundreds of millions of simulated years. Modern computing power has made such simulations possible, and the results have consistently supported the existence of a distant, massive comet reservoir as a natural outcome of solar system formation. The Oort Cloud is not a theoretical convenience. It is what the physics of planetary formation predicts, and the comets we observe are the physical evidence that the prediction is correct. The precise total mass of the Oort Cloud is one of the great uncertainties in solar system science. Estimates range from a few Earth masses to as much as 40 Earth masses, with most researchers favoring values somewhere in the range of 5 to 10 Earth masses. The uncertainty comes from our inability to directly observe the cloud and the need to extrapolate from the relatively small number of long-period comets that reach the inner solar system. The number of comets that reach the inner solar system in any given year is only a handful, but this represents only a tiny fraction of the total cloud, because most cloud objects are on stable orbits that will never send them inward on human timescales, and because many comets that do get nudged inward are destroyed before they become observable, falling into the Sun or being ejected by planetary gravity before they can be detected as bright naked-eye objects. The true flux of Oort Cloud, objects entering the inner solar system, is estimated to be much higher than the handful we detect as spectacular comets each year. There is also the question of which comets we detect versus which comets actually arrive. Bright comets that develop large coma and tail structures are the ones that attract attention, but they represent only the largest and most volatile-rich objects. Smaller comets may arrive in large numbers and pass through the inner solar system virtually unnoticed, detectable only by the most sensitive survey telescopes. As survey technology has improved, the rate at which faint comets are detected has increased dramatically, and this trend will continue as next-generation surveys come online. The Vera C. Rubin Observatory, which began full operations in the mid-2020s, is expected to discover tens of thousands of new comets over its 10-year survey mission. Most of these will be faint and small, not the spectacular naked-eye objects of popular imagination, but scientifically, they will be enormously valuable. The statistical properties of this expanded catalog, including orbital parameters, compositional signatures, and size distributions, will provide far more precise constraints on the structure and mass of the Oort Cloud than we currently have. One of the most interesting questions that an expanded comet catalog might address is whether the Oort Cloud has a uniform population throughout, or whether there are regions of higher and lower density corresponding to gravitational structures we have not yet characterized. Stellar passages through the cloud could create streams or filaments of objects on similar orbits, analogous to meteor streams in the inner solar system. If we observed clusters of comets arriving with similar orbital parameters, this could allow us to trace back the perturbing event that sent them inward, potentially identifying past close stellar encounters from millions of years ago. This kind of forensic astronomy is not unprecedented. Astronomers have already used the orbital parameters of long-period comets to constrain the rate and nature of stellar encounters with the Oort Cloud over geological timescales. The passage of Scholz's star 70,000 years ago, for example, was confirmed partly through analysis of the orbital parameters of outer solar system objects that show evidence of having been perturbed at that time. As more data accumulates, the Oort Cloud becomes an archive of the Sun's encounters with other stars going back hundreds of millions of years. The Sun's motion through the Milky Way is not entirely smooth and uniform. The galaxy has structure, including regions of higher stellar density, the spiral arms, and regions of concentrated gravitational mass, like molecular clouds. As the Sun passes through these structures over the course of its 225 million-year orbit around the galactic center, the perturbation rate on the Oort Cloud changes. Crossings through the galactic plane, where the density of stars and other mass is highest, may trigger comet showers. The current position of the Sun, just north of the galactic midplane, means we are in a relatively quiescent period, but this will change. Astronomers have estimated that the Sun crosses the galactic plane roughly every 30 million years, oscillating up and down through the disk of the Milky Way like a slow wave. Each crossing brings the Sun into a region of higher stellar density and stronger galactic tidal forces, potentially intensifying the perturbation of the Oort Cloud. Oort Cloud and extinction events on Earth may also operate through a more indirect route. Large comet impacts of the scale that could cause global mass extinction events are far rarer than smaller impacts, but far more consequential. A comet nucleus 10 kilometers in diameter striking Earth would release energy comparable to billions of nuclear weapons, trigger immediate firestorms over continental areas, inject enormous quantities of dust and aerosols into the stratosphere, blocking sunlight for years, collapse food chains, and potentially cause the extinction of most large species on the planet. The most famous mass extinction in Earth's history, the end Cretaceous event 66 million years ago that killed the non-avian dinosaurs, was caused by an impactor roughly that size. Current evidence suggests the object that caused this extinction was an asteroid from the main belt, not a comet. But the same physical scenario could, in principle, play out with a long-period comet arriving from the Oort Cloud. Such an object might provide only months of warning before impact, compared to the potentially years or decades of warning we might have for a known asteroid on a collision trajectory. The search for long-period comets far from the Sun, before they enter the inner solar system, is therefore not just scientifically interesting. It has practical implications for planetary defense. Every long-period comet discovered farther from the Sun is a comet that has been identified before it has had time to develop a bright coma and tail, and before it has become an imminent threat. The earlier we detect an incoming Oort Cloud object, the more options we have for responding. Current survey programs detect most comets relatively close to the Sun, inside the orbit of Jupiter, after they have already developed significant activity. This gives us typically a year or two of warning for particularly dangerous objects, and much less for the smallest and faintest ones. Future surveys designed specifically to detect objects at greater heliocentric distances, perhaps using space-based infrared telescopes optimized for detecting the faint thermal glow of cold comets in the outer solar system, could extend warning times dramatically. The case of comet C2025R3, detected in 2025 by the PAN-SDARS survey, is instructive. PAN-SDARS detected the comet while it was still in the outer solar system, at a distance where it had barely begun to develop activity. This gave astronomers nearly a year to observe its approach, refine its orbit, and predict its behavior near perihelion. If the same comet had been discovered weeks or months later, when it was already inside the orbit of Venus, the scientific opportunity would have been much smaller, and the response time for any hypothetical threat scenario would have been negligible. The long-term scientific program of mapping the outer solar system, including the deep searches for Hills cloud objects and the ongoing monitoring of long-period comets, is therefore both a fundamental science effort and a practical investment in our ability to understand and monitor the hazardous objects that exist in the outermost reaches of our solar system. There is also a fascinating philosophical dimension to the Oort Cloud that is worth dwelling on. For most of human history, the night sky represented the totality of the observable universe. The stars were fixed points of light on a celestial sphere. The planets were wanderers among the fixed stars. The sun was the giver of light and heat. This picture was elegant and comprehensible, even if its physical basis was not understood. Over the last few centuries, that picture has been replaced with a far stranger and more expansive one. The stars are other suns, at distances so vast that light takes years to cross them. The Milky Way is a galaxy containing hundreds of billions of stars. The universe contains hundreds of billions of galaxies. These revelations happened gradually, each one expanding the known universe by orders of magnitude, each one requiring a fundamental revision of our sense of scale. The discovery and characterization of the Oort Cloud represents a smaller but philosophically similar expansion. It reveals that our own solar system, which we might be tempted to think we understand well after decades of planetary exploration, extends far beyond anything we have directly explored. The planets, all of them from Mercury to Neptune, exist in a tiny inner region that represents a fraction of a percent of the solar system's total radius. The Kuiper belt is somewhat larger, but still tiny compared to the Oort Cloud. The cloud itself extends almost to the nearest star. We live inside a structure that is almost unimaginably vast, most of which is invisible, uninhabited, and unexplored. The solar system is not a planetary system with a little bit of extra debris at the edges. It is a planetary system embedded in an enormous comet cloud, and the planets are a small detail at the center of a much larger story. Jan Oort had no way of fully appreciating the implications of his 1950 paper when he wrote it. He was responding to a specific observational puzzle, trying to explain the orbital distribution of long-period comets. The solution he proposed, a distant spherical reservoir, was elegant and well supported, but the full magnitude of what he was describing was perhaps not immediately obvious. Today, 75 years later, we understand the Oort Cloud in the context of solar system formation, galactic dynamics, planetary defense, the origin of life, and the long-term fate of the solar system. Each of these connections adds a new layer of significance to a structure that, at first glance, might seem like a minor footnote to the story of the planets. The Oort Cloud is also a reminder of how much remains to be discovered. In an era when it can sometimes feel as though the solar system has been mapped in exhaustive detail, with orbiters around every major planet, landers on Mars and the Moon and asteroids, flyby missions to Pluto and the Kuiper belt, and 2 spacecraft now in interstellar space, the Oort Cloud stands as a vast, untouched wilderness. We have barely knocked on its door. We have never entered it. We will not enter it for centuries, perhaps millennia, with any technology we can build today. This is not a failure. It is a measure of the ambition required by the scale of the universe. The universe is not sized for human timescales. It does not fit in a single lifetime, or a single civilization's lifetime, or even the entire duration of life on Earth. The Oort Cloud will exist for billions of years after humans, or whatever we become, are finished exploring it. But in the meantime, the comets keep arriving. Each one is a gift from the deep past, a frozen messenger from before the Earth was born, carrying the chemistry of the early solar system through 4.5 billion years of cold preservation to arrive, briefly illuminated, in the inner solar system where we can see it and study it and wonder at it. That is what the Oort Cloud is. It is time preserved. It is history made visible by the accident of a gravitational nudge from a passing star millions of years ago. And every time we look up and see a comet gracing the night sky with its pale, silent light, we are looking at the Oort Cloud announcing its existence in the only way it can, by sending us one of its children. The science of the Oort Cloud is still in its early stages. The cloud's total mass is uncertain. Its inner structure is poorly constrained. The proportion of rocky to icy bodies is unknown. Whether it contains undiscovered large objects, dwarf planets, or even a captured rogue world remains an open question. The rate at which the galactic environment perturbs it, and whether those perturbations correlate with geological events on Earth, is still debated. The mechanisms by which long-period comets are captured into short-period orbits are understood only in broad outline. These are not minor technical details. They are fundamental questions about the structure of our solar system, its dynamical history, its influence on Earth's habitability, and its place in the broader galactic environment. Answering them will require new telescopes, new spacecraft, new computational models, and new generations of scientists with the patience and ambition to study the farthest, darkest, most ancient parts of our cosmic neighborhood. The journey continues. It began with Voyager 1 crossing the heliopause and sampling the interstellar medium for the first time. It will continue when the first probe designed specifically for the outer solar system reaches the Hills Cloud, whenever that day arrives. And it will continue after that, as we push further and further into the dark, following the comets back to their source and learning, one frozen messenger at a time, about the vast invisible structure that wraps around everything we have ever called home. Consider what it means to study a structure that no human instrument has ever directly imaged. Every other major feature of our solar system has been photographed. The planets have been observed from orbit. The asteroids have been visited. Comets have been landed on. Even Pluto, which was thought for decades to be too small and distant to reveal surface details, was photographed in stunning clarity when New Horizons flew past it in July of 2015, revealing a world of nitrogen glaciers, towering mountains of water ice, and a distinctive heart-shaped plain that became instantly iconic. The Oort Cloud alone has never been photographed. Not a single component of it has been resolved into even a point source by any telescope currently in existence. This is because of the physics of detection, which are stark and unforgiving. The most powerful optical survey telescope ever built, the Vera C. Rubin Observatory, can detect objects as small as a few kilometers in diameter in the Kuiper belt at 40 to 50 astronomical units. At the inner edge of the Oort Cloud, 2,000 astronomical units away, an object would need to be roughly 40 times larger or several hundred kilometers in diameter to produce the same apparent brightness. Only the very largest Oort Cloud objects, if any exist at that scale, might be detectable. At 10,000 astronomical units, the distances associated with the main Oort Cloud, the required size jumps to thousands of kilometers, comparable to major dwarf planets. We would need to be very lucky to have an object that large sitting at that distance in the right position to be detected. And even if such an object existed and we stumbled upon it, it would appear as nothing more than a faint, slowly moving point of light distinguishable from background stars only by its motion over weeks or months of observation. The Vera C. Rubin Observatory will nonetheless represent a major advance in our ability to probe the outer solar system. Its design combines a large collecting area, a wide field of view, and a highly sensitive digital detector array to systematically image the entire accessible sky repeatedly over 10 years. Every moving object detected in multiple images can be tracked, its orbit computed, and its distance estimated. Over the course of the survey, it is expected to discover a number of Sedna-like objects, large bodies on highly elongated orbits that take them from deep in the outer solar system inward to perihelia at a few hundred astronomical units. Sedna itself is one of the most interesting outer solar system objects known. Discovered in 2003 by astronomers Michael Brown, Chad Trujillo, and David Rabinowitz, Sedna has a perihelion of about 76 astronomical units, far beyond Neptune, but an aphelion estimated at around 900 to 1,000 astronomical units. It never comes close enough to Neptune for that planet's gravity to have placed it on its current orbit. Something else must have been responsible, perhaps a passing star in the early solar system, or the gravitational influence of the hypothetical planet 9, or perhaps an encounter with another star during the Sun's birth cluster phase. Sedna's orbit is often described as being in the inner Oort Cloud region, even though it is much closer than the main Hills Cloud is thought to be. It might be a member of an inner population that connects the Kuiper belt to the Hills Cloud, a population sometimes called the extended scattered disk. If Sedna is not unique, but representative of a large population of similar objects, then there may be thousands of Sedna-like bodies in orbits ranging from the outermost Kuiper belt to the inner Hills Cloud, creating a more gradual transition between these regions than the simple two-component model suggests. The discovery of Sedna-like objects is scientifically important for another reason. Their orbits, which take them on long, slow loops from the inner hills cloud region to several tens of astronomical units, mean they spend most of their time at distances where they are not actively sublimating ice. They are therefore relatively pristine. When such objects come to perihelion, any surface changes from solar heating will be superficial compared to the deep frozen interior. Studying a Sedna-like object at perihelion could provide information about the chemistry and structure of outer solar system bodies in a way that complements what we learn from comets that have made many close passes to the Sun and have lost much of their original surface material. The science of outer solar system exploration is not standing still. Even without direct access to the Oort Cloud, astronomers are continuously refining their models using a combination of observational data, dynamical simulations, and laboratory analysis of meteorites and cometary samples. The Stardust mission, which captured cometary dust from Comet Wild 2 in 2004 and returned it to Earth, and the Rosetta mission's extended study of Comet 67P Churyumov-Gerasimenko from 2014 to 2016 provided direct compositional data on short-period comets. While these comets are from the Kuiper belt rather than the Oort Cloud, some of the same basic materials are present, and studying them informs our understanding of what Oort Cloud objects might be like. Laboratory analyses of cometary samples from Stardust revealed that Comet Wild 2 contained a surprising abundance of high-temperature minerals that must have formed in the inner solar system, very close to the Sun, where temperatures are high enough to vaporize rock and recondense it into crystalline silicates. These minerals should not have been present in a body that formed in the cold outer solar system. Their presence indicated that material from the very inner regions of the young solar system was transporting outward by mixing processes during the early formation era, blending with icy outer solar system material. If this mixing occurred in the Kuiper belt, it almost certainly occurred in the outer solar system populations as well, including the precursors of the Oort Cloud. This would mean that Oort Cloud objects are not exclusively cold outer solar system material, but may contain contributions from throughout the young solar system, including refractory minerals formed near the Sun billions of years ago. The Oort Cloud, in this sense, may be a repository of the full compositional range of solar system material, mixed together and preserved in cold storage for 4.5 billion years. The Rosetta mission was particularly revealing about the complexity of cometary surfaces and the variety of processes that shape them. The nucleus of Comet 67P was found to be a contact binary, two separate lobes joined at a narrow neck, suggesting it formed from the gentle collision of two distinct objects early in solar system history. Its surface showed a wide variety of terrains, from smooth plains of fine-grained material to rough, angular cliffs and boulders. The comet lost hundreds of thousands of kilograms of material per hour at peak activity near perihelion, yet revealed that even after multiple perihelion passages, its interior retained highly volatile compounds like molecular oxygen and noble gases that would not survive unless they had been trapped at very low temperatures since formation. These findings paint a picture of comets as complex, geologically active bodies despite their small sizes, and as repositories of extremely primitive material that has survived in cold storage since the solar system's formation. Long-period comets from the Oort Cloud, which have made far fewer perihelion passages than short-period comets, would be expected to be even more pristine. The interior of a long-period comet arriving for the first time in the inner solar system could contain material virtually unchanged since the solar nebula condensed 4.5 billion years ago. This is why missions like the Comet Interceptor, developed by the European Space Agency with contributions from the Japan Aerospace Exploration Agency, are so scientifically exciting. The spacecraft is designed to be placed in a gravitationally stable waiting orbit at the Earth-Sun Lagrange point 2, roughly 1.5 million kilometers from Earth in the direction away from the Sun. There it waits, watching the sky, ready to be redirected when a sufficiently interesting target is discovered with enough advance notice. The target of primary scientific interest would be a dynamically new comet arriving from the Oort Cloud for the first time. Such a comet would have a near-circular orbit that has been gradually perturbed into an elongated one by galactic tides or stellar encounters, sending it on its first inbound journey. Before this visit, it would have been at temperatures near absolute zero for billions of years, its surface and interior essentially unchanged since the beginning of the solar system. A mission to such an object, flying through its coma and past its nucleus, would sample material as close to primordial as anything accessible in the modern solar system. The technical challenges are significant. The comet's orbital parameters would not be precisely known until shortly before the mission launch window closed, requiring rapid mission planning and execution. The comet's activity level, which determines how hazardous the environment near the nucleus is for the spacecraft, cannot be predicted far in advance. The spacecraft would need to carry instruments capable of characterizing gas, dust, and plasma environments simultaneously. But the potential scientific return justifies the engineering challenge. If Comet Interceptor or a successor mission succeeds in flying past a dynamically new long-period comet, it will be the closest science has ever come to directly studying the Oort Cloud. The comet is a piece of the cloud. Its composition, structure, and history are the cloud's composition, structure, and history made tangible and accessible. In a very real sense, sending a spacecraft to intercept a long-period comet is the closest thing we can do, with current technology, to visiting the Oort Cloud itself. The scientific importance of understanding the Oort Cloud extends beyond our own solar system in one more critical way. The detection and study of extrasolar comets and the search for exo-Oort clouds is becoming an active area of research as exoplanet science matures. We have now confirmed the existence of thousands of planets orbiting other stars. The next frontier is characterizing the full architecture of those planetary systems, including their outer regions. The transit photometry method, used by the Kepler and TESS space telescopes, is most sensitive to planets orbiting close to their host stars. The direct imaging method, which has successfully photographed a few giant exoplanets orbiting far from their stars, is beginning to access the regions comparable to our own outer solar system. But the Oort Cloud analog around another star is far beyond the reach of any current direct imaging capability. Indirect evidence for exo-Oort clouds comes from several directions. White dwarf stars that show heavy elements in their atmospheres, elements that should sink out of sight in the white dwarf's atmosphere within thousands of years due to gravitational settling, are thought to be accreting material from leftover planetary system debris. A significant fraction of the accreted material has compositions consistent with icy bodies from the outer regions of the former planetary system. This is indirect evidence that these systems had Oort cloud-like reservoirs that are now being disrupted by the changed dynamics following the host star's death. Infrared excesses around mature stars, excess emission at wavelengths corresponding to warm or cold dust, sometimes indicate the presence of extended debris structures. If some of these structures extend to thousands of astronomical units, they would be consistent with exo-Oort cloud analogs being actively perturbed and sending material inward. Distinguishing this from other sources of infrared excess requires careful modeling, but the signatures are potentially present in existing datasets. The study of these distant reservoirs around other stars will accelerate dramatically with future telescopes. The proposed infrared successor to the James Webb Space Telescope, along with next-generation ground-based extremely large telescopes, will push the sensitivity of direct imaging to lower luminosities and greater separations, potentially beginning to characterize the outer architecture of nearby planetary systems in ways that are currently impossible. Each advance in this direction will also refine our understanding of our own Oort cloud by providing comparative data from other systems. If we can establish that the Oort cloud structure around the Sun is typical for a star of its mass and age, or if we find that it is unusual in some way, we will understand our own solar system better. Comparative planetology has always been one of the most powerful tools for understanding Earth. Comparative solar system architecture, including the comparison of Oort Cloud structures, will be equally powerful for understanding the outer solar system. The story of the Oort Cloud is, at its core, a story about the limits of human knowledge and the tools we use to push beyond them. Jan Oort could not see the cloud he described in 1950. He inferred it from orbital mechanics and cometary data. Generations of astronomers since then have refined his inference, adding computational models, infrared surveys, dynamical simulations, and the precious handful of real comet samples we have managed to collect. None of them have seen the cloud directly. All of them have known it was there. This kind of confident knowledge in the absence of direct observation is one of science's most powerful achievements. It means that our understanding of the universe is not limited to what our eyes or our instruments can directly resolve. It extends to what our models and our data allow us to infer. The Oort Cloud is one of the clearest examples of this in all of solar system science. And when, one day, a future telescope finally resolves a Hills cloud object for the first time, or future spacecraft captures in situ data from the vicinity of a dynamically new comet, or a future survey detects the first confirmed exo-Oort cloud around a nearby star, those moments will be additions to a long chain of understanding that stretches back to a Dutch astronomer in 1950. Looking at orbital data and recognizing the shape of something vast and ancient hiding at the edge of the solar system. The outer darkness is not empty, it is full of time, and we are only beginning to learn to read it. There is one more dimension to the Oort Cloud worth exploring in depth, which is the question of what it can tell us about the solar system's future rather than just its past. We have spent considerable time looking backward, tracing the cloud's formation and the history encoded in its icy contents. But the cloud is also a dynamic structure that will continue to evolve, and understanding its future evolution is part of understanding the solar system as a whole. On timescales of millions of years, the primary driver of change in the Oort Cloud is the stream of stellar passages through or near it. On average, a star passes within 1 light year of the Sun roughly once every 100,000 years. Most of these are distant enough to cause only minor perturbations to the outermost cloud objects. But on timescales of tens of millions of years, the cumulative effect of many such passages continuously reshapes the cloud's outer regions. Objects are stirred into inbound orbits, depleting certain populations while leaving others untouched. The Sun's passage through the Milky Way's spiral arms, occurring every few 100 million years, brings it into regions of higher stellar density where encounter rates increase. During these periods, the Oort Cloud is more actively stirred, producing higher rates of long-period comet delivery to the inner solar system. Between arm crossings, in the quieter interarm regions where the Sun currently resides, the encounter rate is lower and the cloud is more stable. Over billions of years, the outer cloud will be gradually depleted. Stars passing through it or nearby will remove weakly bound objects, sending some inward to the inner solar system and ejecting others into interstellar space. The inner Hills cloud, more tightly bound, will deplete more slowly, but it too will lose material over time, both to stellar encounters and to the gradual comet delivery to the inner solar system. The rate at which the cloud depletes over the Sun's remaining 5 billion-year main sequence lifetime depends on factors we cannot currently predict precisely, including the exact sequence of stellar encounters the Sun will experience. Computer simulations suggest that a substantial fraction of the current Oort cloud could be lost over the next 5 billion years, not catastrophically, but gradually, one encounter at a time. As the Sun enters its red giant phase, the situation changes dramatically. The Sun's luminosity will increase by a factor of thousands over a relatively short period, geologically speaking, perhaps 100 million years. The intense radiation will begin to sublimate cometary ices at distances far greater than today. Objects that are currently frozen solid in the Oort cloud will begin to slowly lose their volatile content even without approaching the Sun. The cloud will begin to become a source of diffuse gas and dust surrounding the solar system, rather than a reservoir of intact icy bodies. As the sun sheds its outer,